Professor Olof Ramström, member of the Nobel Committee for Chemistry. What is this year's prize about?
This year's prize is about metal organic frameworks. And this is a type of structure, a porous structure, which our laureates have developed over a number of years from very basic principles. So what they actually have done, and I can show you a little model here, they have taken two different types of components. So one component is a metal, or a metal ion, or a metal cluster. And then you link that together with what we call organic ligands, organic linkers. So this orange one here is an organic molecule. These are carbon-based molecules. And you link them together and you mix them together in a solution. And then these two will find each other in a particular pattern and form three-dimensional materials, such as maybe this one. And this material is very interesting because here you have cavities inside, you have relatively large cavities inside, and they can be used to capture small molecules, like this is a water molecule model, and they can go inside the cavities and be absorbed by this framework, this metal organic framework, and then you can use it or you can release it when you need it. If you want drinking water, you can, for example, release it. And so this is exactly what the laureates have been working on, to make such materials and to formulate principles and concepts how to deal with those materials.
And why is this so important?
Well, when it comes to these kinds of structure, these are so-called porous materials. They have a multitude of different applications. So we use porous materials all the time in society today. For example, when it comes to handling gases of different types, so gas storage or gas separation. For example, when you work with something, you need to separate carbon dioxide from something else, then you use porous materials. And porous materials are used in many, many different aspects. And that's why this is so important, because here we have a new type of material where you can actually tailor the structure very, very, very exactly to get exactly the right size of the cavities, so they fit perfectly for one type of gas or one type of molecule. And also you can build in, you can modify these structures so nicely, so you can actually have them do something for you. They can, for example, have groups inside that can react with the molecules that come inside and make chemical reactions. So that means that you, for example, can degrade harmful substances in the air. So the harmful substance comes in, and then you have a catalytic group that we call it inside that can then degrade this molecule and then release it as a harmless compound.
So you can get clean air.
You can get clean air. So that's a very good application for this.
What other applications? You said water, but what other?
Yeah, so there are so many applications, and we have seen so many applications, right? So for example, people have been working very, very strongly to be able to use such materials also in biological sciences, for example, as drug delivery matrices. So they have been studying these. These are materials that can hold drug molecules, and then when you apply them to a patient, for example, they can release the drug at a certain time and place where you need the drug, right? So there is a lot of work going on in that direction. Also, you can use these materials for sensing, for example. So you can have a material that gives you a signal when a molecule comes in and binds into it. Then you can get the signal, and then you can analyze, and you can see if that compound is actually in the environment.
Many applications. Could you tell us a little bit about the laureates? I mean, you were there when they made the call.
Yes.
How was the course? There are 3 laureates.
There are 3 laureates, and it's always very interesting to call the laureates. And also in this case, it was very, very interesting. So the laureates, they are always surprised, and they're always taken by surprise. We had one laureate who was just in between 2 flights. He was going to Brussels. And he was just between switching flights when we called him, and of course that made him very surprised, and also, so they're always very, extremely surprised and very, very happy, and
what do they say?
Very moved.
Any particular thing?
Yeah, they say, all 3 of them say that they were very, very happy to share the prize with the other 2, because all 3 of them are friends. So it's a very nice thing to
In very short, if you should tell us a little bit about the laureates? Who are they?
Oh, the laureates. So we have 3 generations, you can say. We have Richard Robson, who started this, you can say, a long time ago now. And he has been working mostly in Australia in his career. And then we have Susumu Kitagawa, who's been working in Japan for many years. And then finally we have Omar Yagi, who is originally from Jordan, but now has been working in the US for many years.
If you would finally summarize this prize in 30 seconds, what would your pitch be?
That's a very tough question to answer, but I can tell you, I'm very, very impressed by their work, because what they have been doing is that they have taken basic principles of chemistry, we call this coordination chemistry, and they have been able to build such remarkable materials that can do so much, and I'm really impressed by that.
Thank you so much, Professor Olof Ramström, for explaining this year's chemistry prize for us. Thank you.
Thank you for having me.